Hey, so my project is on hybrid geolocation using street clip and boundary-based regression. My name is Sham Patel, and the problem description is geolocation or image geolocation is determining the exact geographic coordinates of an image based solely on visual content. So this is simply just saying that if you have an image, try and how do you geolocate this image on Earth? With only the values on the image, so just the image itself, how do you find exactly where this is on Earth? Now, there's a few existing approaches. More recently, there's been a surge in these papers, and there's actually been very, very good progress being made. And so the first two, large vision language models and retrieval augmented generation, were used in a paper a few years ago. But how it works is basically you have text data and then you have visual encoders, and those are paired together to basically transform text into imagery, and then it's combined with RAG, retrieval augmented relation generation. And RAG is basically, you can think of it as a massive library that just stores all these files or all these data files, and you can pull those out and then compare those with what you get from LVLMs. Now, a big con for this is you need a lot of storage space and a lot of computational resources to implement this RAG because of how much data you need to store in there. So it's just you just need too much, or you would just be you would be left struggling because of how computationally heavy this is. The next approach is CNN, which is convolutional neural network, and that's paired with ground and satellite imagery. And how this works basically is CNN pulls out patterns from data or clusters of data, and it would basically look at a ground image and pull out a pattern from there, and then look at the satellite image and then try to figure out a similar pattern from there, and then connect them together for more accurate precision. But an issue here lies with if you have ground and satellite imagery that aren't exactly linked together, and you're training your model on that, it's gonna have run into a lot of issues and then give you false data or false predictions. So that's something you need to look out for. Another thing is satellite imagery is very very expensive to obtain if you're buying it, and also very very large to store that. So yeah, you just require a lot of computational resources. And then the last two, or second last two, is geocells and novel loss function based on Haversine. So this is actually from a research paper that created this model called Pigeon. Now this was released about 8-9 months ago, and I would say is probably the best AI model for geolocation that we have. It is extremely good. They used it to compete against the one of the best GeoGuessr players in the world. And GeoGuessr is a game basically where you geolocate yourself based on where it puts you on Earth, and you just have Street View to look around you. But the one of the best players on Earth, a very popular YouTuber, you went against this AI algorithm and he lost. So yeah, it's very very powerful. And how they managed to achieve that is they implemented geocells. Now, geocells you can think of as just a massive grid that covers the whole globe. Originally, researchers did do that, but they created a uniform cell. So basically the same size cell, copy and paste it all around the globe. So it really wasn't accurate because it would group different countries and get different regions together. And it was just, yeah, there was no a variation in it. So what they did was they created a hierarchical, non-uniform grid of cells. And how they did that is they pulled out country borders, and they used the borders as grid cells. So each country had its own cell. And I'm assuming larger countries had a few cells. Um, and so, and how they managed to like even go more in depth than that, because when you pull out the borders of the countries, you can go further in, and they actually did the same, I believe, for cities too, and regions. And so how they did that is they implemented their own novel loss function based on Haversine, the Haversine loss function. And what it did differently was it punished the model every time it made a mistake, and the repetitive punishments just made the model more accurate because it's learning by being punished. And so yeah, that's I would say the best model out there. But the downsides of it is it's a very, very computationally expensive. I believe they used 4 A100 GPUs and they still had like execution times of like 10 to 12 hours, like something crazy like that. And there was just no way for me to implement something like that out the box. One, because it's so complex and complicated with everything that they did, that it was very hard for me to understand. Secondly, is it's just very, very heavy that even like if you require 4 A100 GPUs to like run it, like I wouldn't be able to use that. So I decided to go for a hybrid approach, and I used the last approach that's called generalized zero-shot learning. And this is implemented in a model that I used, a classification model called StreetClip. Now, StreetClip uses generalized zero-shot learning, which basically treats seen data and unseen data as the same. Even though it's trained on seen data, um, it it's trained in a way, the semantics and the auxiliary features are are made in a way that it treats like the unseen data as though it's seen data, and basically tries to alleviate from having any bias. That's why I really like this model. Another thing is it's trained on 1.1 million images from not just urban areas but also rural areas. So I feel like it's a very broad encompassing model that was perfect for my use case. And so a bit about my approach was, yes, I used a classification model, but I combined it with a regression model, and I used random forest regression for that. And as I was doing my research on that, random forest regression for my use case, I would say was very uh, efficient because it's a very simple approach. It's not heavy at all, and it actually helps because what it does is it does something called bagging, where it has a bootstrap part and then an aggregation part. And what it does, it will get arrays of data and cluster them together through, like it would bootstrap them together, and then it would aggregate them, and it would pull out the average or the average or most common numbers or most common array or most common values from that aggregation. And so basically, it will take a lot of arrays and then dumb it down, like compress it into one common theme that just encompasses all the values. And so I really like that, and I felt like it would help a lot, especially with the computational resources I was working with. So I used that, and how basically they combined together was the classification model would predict a country from an image, and I could have gone further to predict a city, but again, if you have 256 countries and you have 3 cities or 5 cities per country, it just kept snowballing into bigger and longer run times. So I kept it at country classification. Granted, if I did do cities, my accuracies would be much better. So how this works is a classification model predicts the country and then feeds it to the regression model. Now, when the model predicts a country, immediately I have a GeoJSON file that basically has country shapes for every single country, and then country centroid values, which is basically a center value for each country. So once the country is predicted, you'd look at that file and then you'd extract the boundaries of that country as well as the centroid point of that country. Now, this is useful because we combined the data we have with the feature extraction. And so, well, feature extraction just looks at all of the data, image data we have. That's like 15,000 images. So it'll pull out the important features from it. And in the first time I ran it, it pulled out 768 features. Now, the issue with that is that it takes too much time to execute, and especially going further with that, it would just take way too much time, but it's much more accurate. So what I had to do, unfortunately, was I implemented a PCA algorithm that condensed the 768 image features all the way down to 4. So these 4 features are like the most rich features of the image, the most like data rich features compared to like the 768. Even though the 768 has like more um, is more accurate and has better data, the 4 features itself just kind of is like the 768 into 4. So you can imagine how much like data could is lost from that, but it had to be done. And then so what I did was I used those 4 features and then combined that with the geo boundary of the predicted country. And so you would have 6 features then, and then I fed it into the regression model, and then that spat out an original prediction. So just like, hey, this is where it is it should have been in the country, but I ran into some issue where all my original predictions were all clustered together for some reason. I couldn't really figure that out. But once I implemented an adjusted prediction, basically I had the centroid data and I fed that into the regression model as well as the other image features. I got such like better, more accurate results from that. And my thinking is that when you have um, the centroid data of the country implemented into the regression model, it kind of uses that and like gives it a lot of priority and a lot of importance so that it looks around in that region. And for some reason, it didn't do that for the boundary, but it did it for the centroid. Um, and then, yeah, from that, you would get a very accurate score or very accurate point. So let's see the visualizations of this and the other evaluations I ran. So firstly, you have two scatter graphs. The one on the right compares the actual points to the original predictions. And as you can see, it's very clustered together. And on the left, you have the actual points compared to the adjusted predictions. And as you can see, it's very like almost, I wouldn't say 1-to-1, but very close to that. You have some outliers here and there, but for the most part, it's very accurate. And one thing to notice for the blue points, the actual points, is they're very spread out, very sparse. So it's not just all clustered in one area. You can make out like the continents, North, South America, Europe, Asia, uh, Oceania. But yeah, you can make out those different continents. So there wasn't really an issue with the data set that I used, I would say. And then here's another visualization. As you can see, the green is the adjusted points. So all of them are all like towards 0 to 500 kilometers away. So that's very, very good. But on the far right, you can see there's some variation, right? Some of the points are like very, very far off. So there's a lot of variance in the data. So it leads to like misleading results, I would say. But like if you visualize it like this, it's like you can really see for the most part it's very accurate. And so then I made a few categories like within 50, within 500, within 1,000, within 5,000, and then over 5,000. Basically, I wanted to see where all these points would be. So the originals are like way off, like way, way off. So they kind of use that as like a baseline compared to the adjusted. So on the adjusted, you can see majority of them are within that 500 region, which I would say is very good. And then there's a few within the 50-kilometer region, which is excellent. And there's like 500, 700. Those are like the bad points, but I would again blame that on how I cut corners and because of the computational resources and trying to figure out the best way to run these tests fast and find basically small scale versions of things. So I feel like had I used like let's say 768 features that I initially got, had I maybe even implemented some other like more complex techniques than the random forest regression, then maybe like not even maybe, most probably the accuracy would be higher. And then next is a distance line plot that I have. As you can see at the bottom row, all the adjusted distance values are very, very accurate. But if you look between the 10 and 20 image index at the top, you can see the adjusted distance. That one is a massive outlier. It's so far away and it's really pulling the mean up. It's even further than the original distance ones. So yeah, that's just to show how misleading the mean can be. So after this, I created a table and I got the mean for both distances. You can see 6,000 for original and then 2,600 for adjusted. So there's like a 55, I would say 55% jump. And then the closest point, this is very interesting. So the closest point for the original model is 111 kilometers, which is excellent. But then if you look at the closest point for adjusted, it's only 1 kilometer. So that's very, very, very accurate. I was very like happy to see that. That's like very amazing. But again, something that's not so good is that the furthest point for adjusted again is 19,000 kilometers. So you can see the variance is very, very like big, and it's like, yeah, it's pretty scary. And so in conclusion, I just wanted to say that this project was very fulfilling for me. It was very, very difficult. I think I was a bit naive in picking the project that I picked because I had a few ideas like, hey, it's gonna be easy, but no, I was like, well, as soon as I started trying things, like it just didn't work out at all. I spent a lot of times going over like frustration, headaches, trying to implement different out the box models. Didn't work at all. Kept restarting, and yeah, it was pretty painful. But I would say I'm pretty satisfied and fulfilled with the results. Hopefully, in the future, I can revisit this and even like add more novel features and new things where I don't need to cut corners for computational reasons. Like I think I learned a lot, especially in this course. It was my first time ever learning about computer vision, ever learning about even trying to do any type of research, independent research. I've never like written a paper before, like a research paper. It was my first time reading a lot of literature too, so it was very like very very fulfilling. I would say. And then I also created it. These are all of the files that I have, and so I have a UI.py file right here and I use Streamlit. So I also have a GitHub page where I put all of this on. Um, and so all you have to do is run this command. But if you clone the repository, you'll need to download all these from. I used a virtual environment, but you could use Conda too. But you just download all the requirements and then you just run Streamlit run UI.py. And so you'll get prompted to open in browser, but recently, it's not been working, so what you'd have to do is just use the network URL. And so I'll just go ahead and close this. And so yeah, Streamlit is something I came across. I was reading an article, and it's very, very useful. I didn't really know that. I didn't really work with web pages, so I didn't know like you could use cool packages like this. But it was very easy to implement, and it works great. So yeah, you're prompted with like, hey, drag and upload a file image. So I've dropped an image of Lusaka. This is in Zambia. This is in Southern Africa. I used to live here, so I know exactly where this image is. So we can see. So yeah, it guessed it's 70 or sorry, 61% confident that it's Zambia. And yeah, it's so this is the original prediction. It's at 40 and 35. I can tell you that's wrong already. And then this is the adjusted coordinate. So and then you have this interactive map. So you can zoom out and you can see here's the original point and here's the actual point. And then this is the same map as before, but just with the geo shape. And you can see it's very accurate, the geo shape. As for the point, so this point is actually supposed to be here in Lusaka. It's supposed to be like somewhere here. And this is about, I would say 150, so 100 to 200 kilometers away. By road is probably 200. So if you drew a straight line, it's maybe like 100, 150 kilometers away. So it's not terrible, but there's still like room for improvement. But yeah, that's all I had. So thank you.